All right. I'm going to talk to you guys for a little bit about Vamp-IR. I apologize. I made like 80 slides, and I have time for like 7 slides or something like that. So I might go through some of these very quickly or skip some. Vamp-IR is a language for arithmetic circuits. And so a good question is, why do we need a language for arithmetic circuits? An example I can tell you is Anoma has the MASP, which you've heard about several times. And it is written as an arithmetic circuit in R1CS and uses the Bellman library. But we wanted to explore implementing the MASP in other proof systems like PlonK, maybe Halo 2, for instance. So I set out to try and rewrite the MASP in these other libraries. I tried to rewrite the MASP in PlonK first, and it was a big pain. Like Howard, I have spent a lot of time handwriting circuits. I get a perverse pleasure from handwriting circuits, but it's not what you really want to be using your time on. Might be fun to waste an afternoon trying to prove that these two systems of polynomials have the same solution set and so on, but it's not an efficient use of time. And that's kind of what you have to do. These different proving systems, they have a different structure for circuits. So you have to kind of look at the polynomials and do a lot of like grade school math, trying to figure out what are the right polynomials that you need for your system, when really you are describing the exact same thing at its core. So what we want to do with Vamp-IR is have a way of specifying an arithmetic circuit that is universal, so it's portable to any other proving system that uses arithmetic circuits. Vamp-IR is our language for doing this, and it can also serve as a target for DSL. Vamp-IR by itself is, you could call it a DSL, but it's missing some familiar programming things like loops and conditionals and so on. It's a language for expressing circuits, not really a language meant for programming. If you want to do that, you can use a front-end language that compiles to Vamp-IR and then compile from Vamp-IR out to whatever constraint system and proof system you'd want to use. Paul talked a little bit about JUVIX. We want JUVIX to compile to Vamp-IR. We also have another DSL compiling to Vamp-IR called Alucard. It's a Lisp-based DSL. I put question marks here because not confirmed yet or anything like that, but there's some interest from the ZoKrates folks about Vamp-IR as well. I want to show you how arithmetic circuits are represented. Here's 2 arithmetic circuits. An arithmetic circuit is a representation of the computation of a polynomial. So here are 2 arithmetic circuits. They really are kind of like circuits. The name, it's a good name. So I kind of drew these as like printed circuits. These 2 circuits encode the same polynomial, but the computation is done differently, so the circuits are a little different. You can join 2 arithmetic circuits together just by wiring them up. So if you imagine that some kind of voltage is applied to X, Y, Q, R, et cetera, if you wire R to Z, then if you apply a voltage to R, you have the same voltage as Z. I'm not an electrician. I don't know if that's actually true, but in circuits it is. And in fact, this wiring here would be what you would need to do if you were doing a modulo operation by something that is, if you're doing mod 16. You have a range proof over here, which shows that the input to it, the primary input Z, which is connected to R, so it's the same as R. The remainder is less than 16. Arithmetic circuits also specify a system of polynomial equations. So here's that range proof. This is a 4-bit range proof from before. You could also think of it as a system of polynomials like this. Uh-oh. You can also think of arithmetic circuits as a list of gates and wires. Here I have a kind of flattened version of a circuit. It takes 5 inputs. You can see it's Z, A, B, C, and D. And then in a particular order, you apply operations to those inputs. You multiply A times A, B times B, C times C, and so on. So this is another representation of that range proof. And over here we have equations, equalities. This is like wiring. 11 and 0 are equal. That means we're drawing a wire from 11 to 0, and those must take on the same value. Okay. I am going to go through this quickly because I'm starting to run out of time. But I'll show you, this is what Vamp-IR looks like if you want to write in Vamp-IR. Basically, you can define an alias. An alias is a name given to like a sub-circuit. And critically, you can also give it a signature, like a function. The signature tells the compiler how to compose circuits. Circuits don't have like a natural composition, but if you include the signature, you can compose them, and it works fine. All right, so here's some examples. We have a circuit that checks that x is a bool by showing that its square is equal to itself. We have that range 4 circuit from before. I use the bool circuit inside the range circuit, so you can define aliases with aliases inside them. Over here we have 3 different aliases that all use the same expression. We have q times y plus r equals x. This is just like the division algorithm. If you're familiar with div mod, you get a quotient and a remainder. This is that. By changing the signature only, we get 3 different aliases that have different outputs with the same expressions. Expressions are exactly the same, and we are just selecting R, Q, or the pair QR as the canonical outputs for that circuit. Okay, this is the last slide that I'll really explain, and I'll kind of skip to the end. Here I'm defining, I'll explain what we're doing here. This is an example Vamp-IR circuit. The idea is it's a Pythagorean game, an educational game perhaps, where the player submits a triple, A, B, C, and also what their score they think should be. And if A, B, and C form a Pythagorean triple, then the player is granted a score of 1. Otherwise, they get a score of 0. So the player submits their triple and their expected score, and this can be done in zero knowledge. I don't know why, but it can. And the verifier checks that if a squared plus b squared equals c squared, then s had better be 1. And if it's not Pythagorean, then s is 0. All right, so here is the circuit that does this. I have two definitions. One is just for the Pythagorean equation, which, I mean, you can see it right there. And the other checks that x is, this gives you a bit that tells you if x is true or false. Right? So it's like a comparison operator that gives you a bit. All right. So once you define those, then the entire circuit, I know it's behind the couch here, but the entire circuit is on that bottom line. S equals is Pythagorean ABC. And that's the entire thing. That will end up being expanded out through a series of compilation steps, which I definitely don't have time for. But if you're curious about that, come talk to me. We have some promising directions with Vamp-IR, and a couple of them I forgot to put on this slide. One is using algebraic geometry. Since a circuit also defines like a system of polynomial equations, you can use tools from algebraic geometry, ideals, varieties, and Grubner bases to analyze circuits to some extent. We've had some success and some failures with algebraic geometry, but it's really interesting stuff. Also, category theory. This is like very new, but we think we can compile a Cartesian closed category to polynomials, which will hopefully allow us to do some really cool stuff with Juvix compiling to Vamp-IR. It's really interesting. Other promising directions, we are investigating using Vamp-IR with Starks. That's promising, very new also. I think Brian Retford is here. I want to chat. And maybe like SMT solvers to help write circuits as well. Some really cool stuff. Finally, this is the Vamp-IR team. We got some great folks working on it, people with compiler expertise. I'm really excited about the work that these guys are doing. It's great. So thank you. That's it.